Portal, a game where you solve puzzles, some easy, some a bit challenging for some, by using a gun that shoots portals that allow you to travel from one space to another while utilizing what has been given to you in the level or chamber that you are in. What the hell does that have to do with multivariable calculus, also known as Calc 3? There's a fair amount, I would say, but do keep in mind that I am not the most experienced person in this subject. Now, don't take that the wrong way. I mean that as in, yes, I should be passing the class. It's not decided yet. But to be honest, it would be hard for me to go into depth and thoroughly explain what I'm about to talk about, so I'll be keeping it pretty broad. So hey, this is Andric, Sail on YouTube, and I'll be talking today about some things that I learned in Calc 3 that I noticed relates to the Portal video game. Starting off, something I thought of immediately was how the shape of the portals that you shoot out are in the shapes of ellipses. No matter what, the portal will not be in a three-dimensional space or cubed. Since the portal will always be placed against a wall, floor, or roof, it is always bound to a two-dimensional plane or squared, either on the XZ, YZ, or the XY plane. Immediately, I started to remember the vector notation of how to write down an ellipse, and it reminded me of this part of our notes as seen on screen, which looks like a very similarly sized ellipse to the ellipses that are the portals. I wouldn't be surprised that the devs had made the portals using vectors when programming and made them using some similar notation to this. On top of this, I also remembered how to find an area of the ellipse using this formula on screen. A is equal to 1/2 times the integral curve x dy minus y dx, which gives us AB pi. If we find out the distance of A and B, then we can easily get the area of the ellipse for this portal. Something that also intrigued me when noticing how these portals work in-game is how there is a setting in which the game helps lead you into the portal. So, for instance, going into a portal normally, you would have to aim your way into it if you are dropping down onto one to build momentum. The setting basically drags the character towards the portal, that way it's harder to miss, which it reminded me of the vector fields of gravitational forces in chapter 15.1, which makes me think they programmed a fixed point on the center of the portal that has some vectors around it to help you get into the portal without missing. Speaking of momentum, some of the puzzles in the game involve building momentum to launch yourself off of angled surfaces to reach whatever point you are trying to get yourself to. That had definitely reminded me somewhat of how some planes are angled, like in the two pictures on screen, one displaying vectors making a plane and another showing how to get the angle of inclination of such a plane. Now, to get a bit more theoretical, the concept of how the portals work in general is very interesting. You go through some opening shaped as an ellipse that can take you from one point in space-time to another, kind of like a wormhole. There were three-dimensional shapes this concept reminded me of, and that was the hyperboloid of one sheet, the hyperboloid of two sheets, and an elliptic cone. The hyperboloid of one sheet looks similar to that of a wormhole, which is why it reminds me of that kind of idea of going from one point in space-time to another, while the hyperboloid of two sheets and the elliptic cone kind of remind me of how, since it's kind of hard to explain, but because there's like two openings but like one closing, it reminds me of like pretty much the portal when you go through the portal and then end up on the other side. So for instance, the hyperboloid of two sheets, it's like if you had a vector going into the bottom one, up through the bottom one, it would still be going up, back up through the top one. And then for the elliptic cone, it's like the same sort of thing where it's like, if it's side to side, if the vector is pointing to the right, then it'll be going out to the right at that other point. And theoretically, if it weren't one of those shapes and it were like a similar thing where I'm just gonna make a drawing on screen. You have like a certain like cone in one plane, like let's say the XY plane, and then another cone in the YZ plane. It's like it makes me think like if you were to go up, like have a vector go through one of them and it just go out through one of them, then the vector would it's still the same vector, but now it's a different. Anyways, that's just me getting a bit theoretical. Well, let's move on. Throughout Portal 1, when you're solving these puzzles, usually you use a cube a lot of the time. In my gameplay, you may have seen me going back and forth to get a cube to put on a button to progress through the level. Now, I'm not going to talk about any cube, just no normal cube. The main cube I want to take away from this game is the companion cube. Everyone loves the companion cube. And something that this companion cube reminded me of was the section in which we had to find the center of mass for the moments of inertia, and also, so basically just finding the center of mass and the moments of inertia. I said that wrong, my bad. But except in the thing I'm showing you right now, which is our in-class problem given a row of xyz is equal to kz, these side lengths for this rectangular prism was A, B, and C. In this case, the companion cube, if we're looking at it as like just a cube as the name implies, then each side length should be just a length A. So when you're calculating this, it wouldn't be like, for instance, over here where it's like ABC squared. Should just end up being A times A squared, which would just end up giving you like A to the 4th over 2. I believe it'd be something like that. And then after that, you would do your normal stuff, find m sub yx, m sub xc, and m sub x y. And then when you get those, you pretty much get the moments that you need for that. But yeah, and then the moments of inertia are pretty cool too. Pretty much what I'm trying to say is, using this, we can pretty much get these calculations for something like our precious companion cube. One of the last things I'd like to mention is something from Portal 2. There's this new thing added to puzzles to make them a bit more complicated, which is called the Excursion funnel, which heavily reminds me of what a 3-dimensional helix looks like. In fact, it even has a direction and everything. In the picture shown from my class notes, the helix has an orientation that it's being directed upwards. Or, yeah, it has a direction that is being directed towards, and that direction is going towards the positive k-hat direction. And in the in-game excursion funnel, that excursion funnel pushes you in a direction depending on which way it's being oriented. And that orientation can be flipped if you have a switch. So the game probably has it, let's say it's going up like the 3-dimensional helix in our class notes. If you were to press the switch or the button, then it would change its orientation probably from the positive k-hat direction downward to the negative k-hat direction. So instead of pushing you away, it'd reel you in when you're inside of that helix, of course. Not only this, so that's not all. The excursion funnel, if you look closely, is actually a double helix. So this makes me think it's not only like the vector r of t in the last picture, but then it might be some r of t like that. So like that previous r of t plus what I'll call a vector r2 of t, which may equal the same sort of, but the sine and cosine are swapped. So like so it'd be like r of t is equal to 3 cosine t I hat plus 3 sine t j hat plus k hat, and then add that to r2 of t, which I'm saying is probably 3 sine of t I hat plus 3 cosine of t j hat plus positive k hat as well, because they're both oriented in the same direction as per usual. So yeah, that's pretty much my takeaway from that cool mechanic in game. But yeah, that was pretty much all I got for now. Vector calculus can definitely help to see the intricacies on how certain game mechanics may work, as I exemplified here today with the game Portal by Valve. And it's overall something that is just heavily involved in games as a whole, ranging from shooter games like, Fortnite, COD, and many more, to fighting games like 2D fighters such as Street Fighter, Dragon Ball FighterZ, Tekken, or even 3D fighters, because Tekken's technically a 3D fighter, but other 3D fighters pretty much also include this, like Dragon Ball Sparking Zero. When it comes to hitboxes, those are technically vectors as well. But pretty much, I hope this was good enough to earn the extra credit, and that anyone who isn't my professor that's watching this video learned something. I will catch the rest of you in the next video I post, and to my professor, even though I struggled throughout the class, I still had a good time learning from you, and in the end I am very thankful I took this class. I'll definitely come to you for potential questions if I ever have any when working on any future engineering projects that I may have from whatever university I go to, or personal engineering projects, who knows. But yeah, I may contact you, so be on the lookout if you see any emails. But yeah, that's pretty much it. Bye-bye for now.